Just tell you a little bit the important terms in here. So we've written in this kind of beautiful infinite series here, completely, how can I say, equivalent form for our potential, as if we were tabulating it, directly from some monkey trick on the left-hand side. But one of the important characteristics of that series here is that it contains terms which scale differently with the distance of the observation point to the source. So as I increase L, I increase the power of 1 over distance that I have here. So if I am distant enough, I can presumably truncate this series and obtain a very accurate representation of my potential here. Okay, so the understanding that you should develop is where you should truncate this series here. So let's just kind of understand a little bit what kind of thing we're doing. Maybe you can even like redo the drawing to make it more explicit. So I've got my origin here. I've got a blob of charges, and now I'm going to an observation point which is very far away. So if you're like me, with age, vision starts slowly becoming fuzzier and fuzzier, but that comes with a number of advantages. So if I have a slight fuzzy vision from this point here, looking at my distribution of charges, I might not be able to resolve the particular shape that I have here. However, this distribution of charges has a number of simplified characteristics. The first simplified characteristic that you can think of is the average charge that it contains, the total charge that it contains. So if I'm very far away, if there happen to be positive and negative charges right next to each other here, I'm just not going to see them because their potential essentially cancels. But if there is a residual charge, if there is, when I integrate rho here throughout this volume, a non-zero value, then what I'm going to see from this point is essentially a point charge containing this total integrated charge in the blob. Okay? So that's the monopole term. The monopole term looks like the potential of a point charge, this charge being the integrated charge within the volume that I'm considering. Okay? So that's the first approximation. Now, it could be that the total charge is 0. It could be that the total charge inside here is distributed in such a way that the total charge is 0, but I still have some left over. So for example, if I have a case where I have my origin here, and let's say I have a tiny distance between a positive charge and a negative charge here, then this blob has 0 total charge. However, when I measure it, or when I observe it from this vantage point here, if I look very, very carefully, there's something there. But it's not just like a point charge. It's the field of a dipole. Okay, and you remember, so if I have 2 point charges like this, if I have a positive charge like this, I have a negative charge here, the field is going to look, the field lines are going to have these strange shapes here, right? So you'll have that, and then it's going to come back down here. We had written down the potential for 2 point charges like this when we looked at the method of images. Remember, we had the plane, we had a distance d between points here. You can look back at this thing. The point of the dipole here is that the charges cancel, meaning that the leading part of the Coulomb potential gets canceled, but the next part does not get canceled. So here, that's the dipole term here. You've seen dipoles, I hope, in your first course. A little bit, right? So positive charge, negative charge, very, very close to each other. What's the potential for that? It's a bit like the derivative of the original potential. Okay, so in the notes you can you can look. There's well, I don't know. Maybe it's worth doing it in a little bit more detail. So that's what we had, right? So let's say I have this here and this here, and let that be a vector D. Okay. And let me put the origin just right in the middle here. So what do I have here? So that's a positive charge, that's a negative charge. The potential that I have, essentially what it sees is a combination of 1 over the distance of this to this one with the distance of this to this one subtracted, right? So there's R minus D over 2. Minus 1 over R plus D over 2. So that's what I would see. And, you know, if there was a plus Q minus Q, then the potential is just this Q over 4 pi epsilon 0 times this, this whole dependence here. But this here, I can also just expand because R is much further away than D. So if I do the expansion here, the leading terms cancel, and the first correction doesn't cancel. So for example, if I just do the Taylor expansion of that thing, I just get 1 over R, and then in this one here, I would get 1 plus D dot R. Over just the R here. Plus and then minus 1 minus D dot R over R plus blah, blah, blah. And this, as an expansion, the leading terms cancel, but what I get is just this D dot R hat over R squared. Yeah, so it's this, yeah, actually over 2R because I'm doing the square roots of that thing to get the distance. Okay, so what I mean is that the when you do the Taylor series expansion of this, you get a term which is proportional to the size of D, and D has a vector direction, which is pointing from the negative charge to the plus charge like this. So the leading term in this combination of potentials, it doesn't fall like 1 over R, like just a point like potential. It falls like 1 over distance squared, right? Because that's the first correction on the, so that's the case of a kind of simple dipole like this. Now, in the case of a generic charge distribution, this dipole term is just like the moment, like the mechanical moment of these charges. So you integrate the density of charges with the position vector that they're at. And then the dipole term of the potential is just the direction from which you're looking at, dotted into this P here. Okay, so maybe that example illustrates it, right? So that's how you have it here. Let's see how deep I want to go into this. Maybe yeah, maybe let's just discuss this in a little bit more detail for the dipole term. Okay, so in the notes you'll see this whole expansion has many terms up to infinity. You know, monopole, dipole, quadrupole, etc., etc. I even make comments about the labeling of these terms traditionally, which doesn't make sense. Realistically, you are concerned with monopole, dipole terms. Perhaps once in your life you'll do some quadrupole things, but very rarely. So I think only the monopole and dipole are the important ones. The monopole's interpretation is like super clear, so hopefully we don't need to spend too much time on this. But maybe it's worth just talking about this dipole term a little bit more extensively. Okay, so So let's look at the electric field of a dipole. So that's what we're going to do. We're going to add another page here to the space. Okay, so how does the electric field of a dipole look like? So let's just imagine this dipole like this, plus minus. It has a vector d, a distance between the two, like this. And I'm going to take consideration where the distance between the positive and the negative charges is going to decrease, but the charge of these things is going to increase so that the product remains the same. That's going to give me this dipole moment that I have in here. You see, so you see the Q that I have here gets remultiplied into this here. So I've got a product Q times D. So Q times D here is the so-called dipole moment. The product of the two is the important thing. So if I decrease D but increase Q, I get the same dipole moment here. Then there's the notion of the mathematical dipole, which is really when you take the limit of the distance going to 0, charge going to infinity, so that the product of the two remains finite. Okay, so atoms can be good dipoles in that sense, but the mathematical dipole really takes that that product, fixes it, but puts the distance to 0. So essentially, when we talk about a dipole, the important physical characteristic explaining it is really the product of this charge times the